Continue. We are dealing with the properties of the amino acids here. So I can understand this amino acid at certain pH will exhibit this dipolar ion effect. Such dipolar ion effect is called as Zwitter ion. Since it is showing both positive and negative, they are rather behaving like salts, not like simple amines or carboxylic acids. As they are having both negative and positive form here, they can show amphoteric behavior. It means they can react both with acids as well as with bases. So we were discussing about this electroforces, movement of ions with respect to their charge. This is the Zwitter ion in high pH zone. That means in basic medium. Base will abstract the H plus. So from this NH3 plus, one H plus will get abstracted. So that you will have NH2. What charge is remaining? Negative charge is remaining. So when this is available in electrophoresis, the negative charge will start moving towards the oppositely charged electrode, which is positive. In the reverse way, if we are talking about low pH, that means acidic. Acidic medium will be releasing H plus. COO minus will abstract this H plus so that it becomes carboxylic acid. Look at the charge on this species, it's still positive is there. Because it is positive, it is cationic. It will start moving towards a negative electron. Okay?
Yes, yes.
So the point at which, the pH at which the molecule is existing as neutral species or dipolar ion is called as isoelectric point. Usually, they provide you two pKa values. Just have the average of it. That is the isoelectric point of that amino acid. In case they have provided pKa1, pKa2, pKa3. Three are provided. In that case, which pKas should I use? If it is acidic amino acid, if it is acidic amino acid, what do I mean by acidic amino acid? When I talk about an amino acid, basically amino acid will have this unit. This is the major unit. Now here some R could be there. If in this R COH is still available, then I call this acidic amino acid. We know pKa is inversely proportional to acidity. So in the case of acidic amino acid, lower pKa values should be taken. Consider I am having 10, 7, 8. Among them, these two are lower. So use these values to take the average. In case it is a basic amino acid, this R group may have one more NH2. As I said, pKa is inversely proportional to acidity. So we took the lower one, and pKa is directly proportional to basicity. So here what kind of pKas I will use? Higher pKas we will use. 10 plus 8 by 2. Clear till this?
Yes, ma'am.
Right. Now you are going to learn about the peptide formation. Okay. How do they form peptide formation? In what way they are becoming optically active in nature? The case of amino acids. The first amino acid, glycine, is the only optically inactive amino acid. Because when you look at glycine, carbon is bonded with two hydrogens, which makes it achiral. So glycine is the only amino acid which is optically inactive in nature. Other than that, all the other amino acids are optically active in nature. How many amino acids we have? How many amino acids are there? How many are there?
Sorry, ma'am, I couldn't hear you. Can you
How many amino acids are there?
20?
20 amino acids are there. Out of that, only one is optically inactive in nature. When I am putting the D and L form, the NH2 group being in the right hand side is D form of the amino acid. If it is present in the left hand side, it is called as L form of the amino acid. Now let us learn about the peptide formation. Peptide is nothing but amide. What is an amide? When carboxylic acid reacts with amine, when you are going to remove the water, what you form is amide. So here, in this case, this amino acid has both NH2 group as well as carboxylic group. So I am taking glycine here. Glycine is reacting with its own. Remove water. So what do you form? CH2, NH2, CO, NH, CH2, COH. We are able to see the amide has got formed. This is called peptide. This linkage is called as peptide linkage. How many peptide bonds are, what kind of a peptide is that? This is called as dipeptide. Why should I call it as dipeptide? Because two amino acids participated to form this. So I call it as dipeptide. In other words, you can also remember like this. You formed one peptide bond, so add one with it. I call it as dipeptide.
Yes, ma'am.
Okay. So now the question is asking you how many peptides you can form. Say how many tripeptides are formed with glycine, valine, alanine, amino acids. How many can you form? How many can we form, Ra? I'm saying that you should have all the three amino acids here. So it could be gly, val, ala, gly, ala, val, val, ala, gly, val, gly, ala.
Six.
6, correct. Ala, gly, val, ala, val, gly. So you can understand there are 6 amino acid peptide formations are there. Why do we call as tripeptides? So 2 peptide bonds are formed. So 2 plus 1 is 3. So we call as tripeptides. So use 3 factorial here. Okay, let's go for this question. Number of carbonyl groups in tripeptide formed with aspartame, glutamic acid and lysine. They have not told you what is ASP, what is GLU, what is LIS. Since it is provided in NCERT textbook, it is expected for us to remember these things. Also, along with that, you should remember the acid also. So let us look at the acid here. Let me start with glycine, C, H, H and COH. I said it is an aspartic acid. So instead of one hydrogen, I am having CH2COH unit. That means I can see it is acidic in nature. The next one is glutamic acid. Very simple. I am adding one more CH2 in between. Look at this. The next one is lysine. Lysine is basic amino acid. Other two are acidic amino acid, where they have carboxylic acid in it. So here you can see instead of hydrogen, there is a butylamine group that is substituted there. Now the question is asking you, if I am forming a tripeptide in this way, how many carbonyl groups could be there? Calculate it.
Ma'am, 5.
Right. 5 CO groups are there. That's right. Look at this question. Which of the following will not exist in bitter ionic form at pH is equal to 7? In order to remain in its bitter ionic form, we can understand this COH will release H plus and the H plus should be taken by the NH2 because it is having lone pair. Only then bitter ionic form is possible. Here look at this, this will become NH3 plus, COO minus. Similarly here also, SO3 minus, NH3 plus. But the question is, ma'am, is this possible for us to do this easily? Here also NH2 is having lone pair, but we know very well this shows plus M effect, isn't it? Like this. So its lone pair is not actually easily accessible to abstract the H plus. Am I right? Asli, do you understand?
Yes, ma'am.
Right. But still, sulfonic acid is quite a strong acid. It will not wait, or it is not going to wait for the chance to abstract this H plus. So even before this NH2 group is going to participate in resonance activity with the benzene, due to its higher acidic nature, it is able to protonate the NH2. So here it is possible to exist. Here also the possibility is there. Here also definitely the possibility is there. SO3 minus, this will become NH3 plus. But look at this spot. Here the sulfonic acid was very adjacent to amine. Look at this. I am having COH at this position, this is alpha. Beta position only have carboxylic acid. 1 point. Carboxylic acid is not that much acidic like sulfonic acid. Second point. Third point. Here we can see it is definitely involved in the resonance. Ma'am, benzene also will do resonance, ma'am. But benzene is not that much electron withdrawing like carbonate. Here definitely a strong influence of resonance is there. Therefore, this lone pair could not be available on nitrogen. So it will not exist in bitter ionic form. Let's look at this question. Solve this question. your answer?
Is it 5?
What's your answer? 9?
5.
5. That's right. Very good. Check your values for Z1, Z2 and Z3. Is this your value?
Yes, ma'am.
Very good. Super. So that was regarding this topic, amino acids. As I mentioned, you should definitely memorize the amino acids along with their structures. Okay, so we are moving to the last part. Proteins, vitamins, minerals and enzymes.
Till when do we have this class, ma'am?
1 hour session, Ra.
Okay.
Proteins are nothing but polymer of amino acids.
Ma'am, your screen sharing stopped.
1 minute. Proteins are polymers of amino acid. We also call them as polypeptides. That doesn't mean all the polypeptides are proteins here. Okay, so if the number is quite huge enough, then we call it as proteins. So based upon their shape, we classify the proteins here. The first one, depending on their molecular shape. If they are having fibrical things like this, parallelly they are running like this, and they are being held together by hydrogen or disulfide bond, then such proteins are called as fibrous proteins, like this. These proteins are insoluble in water. In this way, God is actually very, very generous on us, because this protein is what is making your hair, the one which is present in keratin. So consider if it is going to be soluble protein. Yes, so whenever you are going to take air bath, your hair will also get solubilized. No one will have hair in their body. Similarly, wool, silk, these are insoluble in nature. That's the reason we are able to wear the cloths made up of wool and silk, right? So remember, fibrous is your hair. It is insoluble in water. Similarly, the one myosin that is present in muscles is also coming under the category of fibrous protein. The next one is globular. The look itself says very spherical, like this. It is spherical shape. It is globular protein. Chains of polypeptide coil. They are coiling themselves. It is not like this to form the nearly spherical shape. This is soluble in water, just the opposite of it. This is soluble in water. Here hydrogen bonds are present between the polypeptide chain. Here hydrogen as well as disulfide bonds are there. Here only hydrogen bonds are there. Examples for globular proteins are insulin, how many amino acids insulin has? Have any idea?
Something like 50.
Correct. They are having 51 amino acids. There are two chains here, A chain and B chain. A chain constitutes 21 and B chain constitutes 30. The case of hemoglobin, there are two alpha chains and two beta chains. This constitutes 141, this constitutes 146 amino acids. So hemoglobin is a red color oxygen carrying pigment in our human body. And albumin, you know, this egg albumin, na? White color, that is albumin. So all these three examples goes for globular proteins. So we have different structural patterns that is being given for proteins. The first one is primary structure, which tells you the number of sequence of amino acid. How many numbers are there in a sequence in the amino acid. So the primary structure of insulin contains 51 amino acids. You can see it's moving. You can see the disulfide bonds are between them. The first primary structure tells you about the number and sequence. Two things it is showing: number and sequence of amino acid. The secondary structure consists of two types: helix, alpha helix, and beta pleated sheets, like this, and sheets which is running like this in a crossed manner. So this is being stabilized by intermolecular as well as intramolecular hydrogen bonds. Inter and intramolecular hydrogen bonds. So you can see the carbonyl group here and the NH2 group, which is leading to hydrogen bonding.
Yes, ma'am.
So here you can see this is a beta pleated sheet here. This is the alpha helix. It is going for right hand screw. So beta pleated sheet can be parallel or anti-parallel. Parallel carbonyl. Parallel means carbonyl NH will be in the same direction. Going for the third degree proteins, 3D structures, interactions of structures by hydrogen bonding. Hydrogen, what are the bonds that bonding is available? Hydrogen bonding, ionic bonding, dipole-dipole interactions, disulfide bond, and London dispersion forces. The diagram is showing us what kind of ionic bond is there, disulfide linkage and hydrogen bonding possibility, van der Waals type of interaction, everything is shown in this diagram.
Yes, ma'am.
The last one, quaternary structure. Example is hemoglobin. So tertiary itself has given us a bright picture here what is happening. So if I'm going to just call them everything together, then which is called as quaternary structure. So many proteins are made of single polypeptide chain. That means same series will be continuing. And they have only three levels of structures. However, some proteins are made of multiple polypeptide chains and also has subunits. And these subunits come together, they give the quaternary structure. Right? So that is about the protein structures here. Let's enter into vitamins now. Shall we enter into vitamins?
Yes, ma'am.
Yes. So in your lower classes you should have studied what are vitamins, in what way they are useful for the human body. So for your normal growth, metabolism, overall health, you definitely need vitamins here. So vitamins not just is going to help you in bodily action, but also boost your immune system. So there are 13 essential vitamins which are categorized into two types here. Water soluble and fat soluble. Water soluble means you have to keep consuming it regularly. Ma'am, today I had this water soluble vitamins like vitamin B and vitamin C. Let me say you had amla juice today. It is not going to get stored in your body. As you urinate and as you excrete, once it is digested, it is gone. You have to drink the very next day the next amla juice. Only then vitamin C will be stored inside your human body. That's the trouble with vitamin C. So two vitamins basically, vitamin B and vitamin C. Among this, vitamin B12 can be partially stored in your body. So it is not actually regarded as water soluble vitamin. Other than that, all the vitamin Bs are considered to be water soluble vitamins. The next vitamin is fat soluble vitamins A, D, E, K. They are being stored in body's fatty tissues and liver for longer periods. So if you are going to consume it, they will be stored. But that doesn't mean you need not take it at all. You need to take it, but not on a regular. It's not required on a daily basis. Let's start learning the names of the vitamins, their actions actually. That's very important. The first one is vitamin A. I'm going to give you a mnemonics to remember the vitamin names. Have you already memorized the vitamin names?
Yes, ma'am, somewhat.
Do you want me to give the mnemonics or can you manage it on your own?
I can manage it on my own.
So this tabular column is provided in NCRT. It's a must for you to learn their names, the deficiency names. Okay. The next one, a very common thing is vitamin C, ascorbic acid. We need to know the structure of ascorbic acid for sure. Please copy the structure of ascorbic acid.
Yes, ma'am.
We are going for the test of proteins here. The first test is called biuret test. For this you use alkaline copper sulfate. It can react with any compound which is having 2 or more peptide bonds. That means amide bonds. So it could be a false test also for proteins. Because if I am having just 3 polypeptide bonds, it will show protein is available. That's not true. So it will give you a false positive basically. But yes, if they are asking for proteins, yes, it will test for protein. The blue color reagent will turn violet in the case of proteins. Also for biuret, you can see that this is biuret. Biuret is nothing but the urea which on dehydration, removal of water. NH2, CO, NH, CO, NH2. You can see 2 amide bonds are there. So it gives a false positive to this compound. The next test is xanthoprotic test. A protein is treated with concentrated nitric acid. It gives orange color in alkaline solution. It gives positive test for aromatic amino acid. So means, ma'am, whenever the amino acid is there and benzene is there along with it, they will be tested for this test. Xanthoprotic test. Next one, Milon's test. Mercury in the presence of concentrated nitric acid gives a white precipitate, which you heat it gives red precipitate. This is a test for proteins. Last one, ninhydrin test. So I am taking a ninhydrin reagent. We have JEE mains question asking us to find the correct complex formation of proteins. So this reagent, when I am treating with amine containing compounds, when 2 moles of it is participating, you can see it is forming this kind of a bond in between. which can give you blue purple color. In which kind of an amine? The amine which is not involved in cycle. If the amine is involved in cyclic compound like proline, then it gives you yellow color, yellow orange product. Right? Let's complete the session with the last question, which is not consistent with the double helical structure of DNA. So according to this Herwin-Chertoff rule, adenine plus this thymine divided by C plus G is not constant. It may vary from human being to human being. So this is true. Adenine plus thymine divided by G plus C, because equal number of adenine and thymine is there, so I can say it's 2x. This is also 2x. So they will be equivalent in numbers only. But when I'm doing the ratio from species to species, it can differ. From 0.4 to 1.9 it can differ. It's not going to be constant here. A is equivalent to T, C is equivalent to G. This is also correct. Then what about this density of DNA decreases on heating? Actually, how does DNA look like? DNA looks like this double stranded. So when I heat it, what would happen? They would dissociate. The hydrogen bonds would dissociate. So this density starts increasing. DNA density starts increasing. So this is the false statement here. Understood?
Yes, ma'am.
Right. I know you are having your exam tomorrow. So I will wind the session with this.